Hello friends, welcome back to my channel. So today we are going to discuss about one of the interesting topic in VLSI testing subject, that is a SCOP analysis. So what is meant by SCOP? SCOP means Sandia Controllability and Observability Analysis Program. So what is SCOP analysis? It is one of the testability analysis technique. So before discussing about SCOP analysis, let's discuss what is testability and what are the different types of testability analysis techniques available. Testability, a relative measure of the effort or cost of testing a logic circuit, is called simply testability. Testability analysis, that means the process of accessing the testability of a logic circuit. If you access the testability of a logic circuit, it is called testability analysis. So what are the different types of testability analysis techniques we have? We have two types of testability analysis techniques. The first one is topology based testability analysis technique. Topology based testability analysis technique, and the second one is the simulation based testability analysis technique. So in topology based testability analysis technique is further divided into SCOP analysis and probability based testability analysis. So in this particular video I am going to concentrate only on topology based testability analysis technique, that is a SCOP analysis. So we have another topology based testability analysis technique along with the SCOP, that is probability analysis technique, which is generally used to analyze the random testability of the circuit. So another testability analysis technique that we have is the simulation based testability analysis technique, which can be performed through statistical sampling. So it can generate more accurate estimates, whereas the major disadvantage of this is it requires a long simulation time. So this is about the testability analysis techniques. Simply remember guys, SCOP analysis is one of the testability analysis technique. Okay, fine. So SCOP means Sandia, S means Sandia Controllability Observability Analysis Program. So let's define what is controllability and observability. So controllability, it is defined as difficulty of setting a particular logic signal to a logic 0 or a logic 1. This is called controllability. What is observability? It is defined as the difficulty of observing the state of a logic signal. Difficulty of observing the state of a logic signal is called observability. So this SCOP analysis was initially developed by Goldstein. Okay, Goldstein developed SCOP testability measures and describes a linear complexity algorithm to compute them. Fine. So let's move further. SCOP measures. We have two types of SCOP measures. So the first one is combinational measures and the second one is the sequential measures. We have two types of SCOP measures. First one is combinational. So another one is the sequential measures. So combinational measures are 3 and sequential measures are 3. Totally we have 6 numerical values or 6 measures. So CC is 0 of S. That means combinational 0 controllability of S. CC 1 of S, combinational 1 controllability of S. CO of S, combinational observability of S. SC 0 of S, sequential 0 controllability of S. SC 1 of S, sequential 1 controllability of S, and SO of S, it is sequential observability of S. So these three are the combinational measures and these three are the sequential measures. The major objective of this particular video is to find out the combinational controllability and combinational observability of a particular logic circuit. This is the main objective of this particular video. We are not going to discuss about sequential controllability and sequential observability in this video. We are going to concentrate only these three: combinational 0 controllability, combinational 1 controllability, and combinational observability of a particular circuit. Okay, please remember this point. In next video I will cover the sequential 0 controllability, 1 controllability, and sequential observability. Fine guys. So please remember these points. These are the very important points before solving the logic circuit by using scope analysis. So the value of controllability measures. So controllability lies between 1 to infinity, whereas observability lies between 0 to infinity. These are the important points. So the combinational 0 controllability and a combinational 1 controllability values of primary inputs are set to be 1. So the sequential 0 controllability and sequential 1 controllability of values of primary inputs are set to 0. Combinational observability and sequential observability of a primary output are set to 0. These are the 3 important points. So in this video I am going to discuss only this combinational controllability now. So this point is very important. That means for a primary inputs, combinational 0 controllability and combination 1 controllability are said to be 1, 1. So if you see the circuit, you can familiar with what are the primary inputs and what are the primary outputs. So let me tell you primary inputs and primary outputs in a given logic circuit. So let's see here. It is a circuit, simple circuit. For your understanding, I have considered this simple circuit. So see here, these are the simple circuit which consists of mainly 3 gates, 2 AND gates and 1 NOT gates. Here I1 and I2, these 2 are the primary inputs. So okay, this O1 is the primary output. These OZ1 and OZ2, these 2 are the secondary inputs. Okay, please remember this point. Fine, you can familiar with primary, what is primary inputs, what is primary outputs, what are the secondary inputs in a logic circuit. So that means if you wanted to solve the combinational controllability and combinational observability of a particular combinational circuit, initially we have to assume combinational 0 controllability and combinational 1 controllability are said to be 1. Okay, so if you solve the example, you can easily familiar with these points. In upcoming slides, I will discuss the problems. Fine. So these are the rules. In order to solve the problems, these 2 tables are very important. So let me discuss about these tables. So if you wanted to solve the problems, these 2 tables are very important. Combinational controllability calculation rules. Okay, so in this particular video, I am going to concentrate only on the how to calculate combinational controllability and combinational observability for a given logic circuit. I am not going to discuss about sequential controllability and sequential observability. That means in this video we are going to familiar with CC of 0 and combinational controllability of 1 and combinational observability. Only these terms we are going to discuss in this video. That's it. So let's see the rules. For a initially for a given circuit, primary input values are set to be 1, 1. I had already discussed this part. So it is one of the rule. Okay, for primary inputs we have to consider the combinational 0 controllability, combinational 1 controllability are 1 and 1, like that. So for AND gate, the 0 controllability is the minimum of input 0 controllability is plus 1. So 1 controllability is sum of input 1 controllability is plus 1. Okay, so it is for AND gate. It is a formula for the AND gate. So see here, NAND gate. So just opposite. So just it is the opposite. Here it is just opposite. If you remember the AND gate formula, NOT gate formula is just the reverse of that. Next, OR gate. OR gate formula is sum of input 0 controllability is plus 1. It is for 0 controllability. For 1 controllability, it is the minimum of input 1 controllability is plus 1. If you remember the OR gate, NOR gate is just opposite. Okay, so NOT gate, input 1 controllability plus 1. It is for 0 controllability. For 1 controllability, input 0 controllability plus 1. So just the opposite. Say for NOT gate. So another thing we have to remember is XOR gate. So it is the for 0 controllability, the formula is minimum of CC1 of A plus CC1 of B, comma CC0 of A plus CC0 of B plus 1. So for one controllability, so it's a formula. If you remember XOR is just the opposite. That means if you remember AND gate, OR gate, so XOR gate, you can remember all this step. So for buffer is not that much important. So in the similar manner, if you want to calculate observability for a given circuit, you have to remember these 4 formulas. For AND gate and NOT gate, same formula. For OR gate and NOR gate, same formula. For NOT and buffer, same formula. For XOR and XOR, it's the same formula. For AND gate, it is the sum of output observabilities and one controllabilities of other inputs plus 1. For OR gate, it is sum of output observability, 0 controllabilities of other inputs plus 1. So if you see the example, you get familiar with all these rules. Okay. So let's see the simple example. Before going to solve a combinational circuits, let's see one simple logic gate. So for example, if they ask to find out the combinational controllability of this particular logic gate, what we will do? Initially, these are the primary inputs A and B. C is the primary output here. So initially, I will consider by default 1, 1. 1, 1. It means a combinational 0 controllability and combinational 0 controllability and combinational 1 controllability are 1, 1. Fine. After that, if I wanted to find out the combinational 0 controllability and combinational 1 controllability at C, what I will do? So I will simply see the formula. What is the formula for the AND gate? If you want to calculate 0 controllability, minimum of input 0 controllability is plus 1. For 1 controllability, it is sum of input 1 controllabilities plus 1. That means if I wanted to find out CC0 of C, what's my formula? So it is minimum of input 0 controllabilities plus 1 for CC1 of C. So formula is sum of input controllabilities plus 1. That means if I want to calculate CC0 of C, so it is a minimum of input 0 controllability. So it is the 0 controllability. It is a 1 controllability. It is a 0 controllability. It is a 1 controllability. Minimum of input 0 controllabilities. What are the input 0 controllabilities? 1 and 1. Minimum of 1, 1 plus 1. Minimum of 1, 1 is 1 only. 1 plus 1, 2. Okay, first one is completed. So we have CC1 of C. That means combinational controllability of C. That means sum of input 1 controllabilities plus 1. Sum of input 1 controllabilities are these two, 1 and 1. Sum of, that means 1 plus 1 plus 1. That means 3. That means here we can get 2, 3. So it is the 2 is the combinational 0 controllability, 3 is the combinational 1 controllability. So for this given logic, simple logic gate, I will find out the combinational 0 and 1 controllability. In a similar way, by default, you can consider 1, 1. If they not mention any value, you can consider a default 1, 1. In similar manner, we can find out. So tell me guys, if here it is 1, 1 by default, it is the AND gate, it is the NOT gate. For NOT gate, for AND gate, what we will get? 2, 3. For NAND gate, it is just opposite, 3, 2. If you calculate OR gate, NOR gate is the simply opposite. If we calculate the XOR gate, XNOR gate is simply opposite. For example, for NOT gate, it is 1, 1. What is CC0 of C? CC1 of A, that means 1 plus 1. CC0, so it is a CC0 of A, that means 1 plus 1. That means a combinational 0 controllability and combinational 1 controllability is 2, 2. If I consider 1, 1 is the default value of a NOT gate. In this way, I can calculate the combinational controllabilities. Okay, by using that particular table. The table and 3 rules are important while solving the problems. So in similar manner, if you wanted to find out the observability, so let's discuss about simple example how to calculate the observability for a particular gate. for your convenience, I will take one simple logic gate. I am not considering this whole logic circuit. I am considering only one simple logic gate. For example, if I wanted to find out the observability for this particular logic gate, what I will do initially, I had already discussed. If I wanted to find out the observability, primary output value is 0. By default, it is 1, 1. It is 1, 1. Okay. Observability at node A. Combinational observability of A is combinational observability of C. That means by default it is 0 plus CC1 of B. That means so other input value. That means so 1 only. 1 is 1. 2. Okay. Here we can get observability is 2. In a similar manner, combinational observability of C by default 0. Combinational one controllability of A. Combinational one controllability of A is 1. 1 plus 1, 2. Here also you can get observability is 2. In this way we can calculate observability. That means for calculating observability we have to follow from backward. So back trace. Okay. In this way we can calculate controllability and observability for a given logic gate. So for your convenience, I will consider one simple logic gate. So for this simple logic circuit, now we can consider now we can calculate combinational controllability and combinational observability. So let's see how to calculate. So here it is, I1 and I2 are the primary inputs. I had already discussed. So this O1 is primary output. OZ1 and OZ2 are the secondary inputs. Fine. So in examination they will not mention 1, 1 in the circuit. By default you can consider it is a 1, 1. So first of all, see this guys, it is a purely combinational circuit without involving any flip-flops and all these things. It is purely combinational circuit which consists of only logic gates. Okay, so first of all you have to confirm that it is a combinational circuit or not. It consists of only logic gates, no flip-flop. Simply it is a combinational circuit. Then we can proceed with the rules. That means if you remember the table, we can simply solve this problem. Okay. So initially you can consider 1, 1, 1, 1 by default. Primary inputs values are 1, 1. If I wanted to calculate combinational controllability, initially I will calculate combinational controllability. After that I will calculate combinational observability. Combinational controllability for this given logic circuit. Initially I will consider 1, 1 and 1, 1. Here it is 1, 1. So here also we can get 1, 1. That means the same way. Okay. So for this you have to calculate at this point. For AND gate, what's the formula from the table? For AND gate, combinational zero controllability is a minimum of input zero controllabilities plus 1. So it is a zero controllability value. For one controllability, our formula is sum of input one controllability plus 1. It is the one controllability formula for only for AND gate. So see here guys, for Z1 AND gate, so minimum of input zero controllabilities. These are the input zero controllabilities. Minimum of input zero controllabilities. That means minimum of 1, 1. Minimum of 1, 1 is 1 only. 1 plus 1, 2. Okay, 2. So next, for if you wanted to find out one controllability, you have to consider this formula. Sum of input one controllabilities. So these are the input one controllabilities. Sum of, that means 1 plus 1, this 1. That means total 3. 2, 3. Okay. Z1, for Z1 it is completed. So here we can get 2, 3. Okay. So here it is, see here guys, it is a NOT gate. Here for input we have considered 0 controllability is 1, 1 controllability is also 1. We have already known for NAND gate from the table. From NAND gate, 0 controllability is So 1 controllability plus 1. So 1 controllability is 0 controllability plus 1. That makes 2 comma 2. Okay. Here it is 2 comma 2. Finally, I can consider at this point. What is the combinational 0 controllability and combinational 1 controllability at this point? So it is also AND gate, simple, same formula. So minimum of input 0 controllabilities. What are the 0 controllabilities? These two, 2 and 2. Minimum of 2 comma 2, 2 only. 2 plus 1, 3. Okay. So next, for 1 controllability, the formula is sum of input 1 controllabilities. Sum of input 1 controllability. So these are the 1 controllability. Sum of 3 plus 2, 5. 5 plus 1, 6. Okay, 3 comma 6 will be the value. So combinational controllability is completed. Okay, let's see guys, if we want to find out combinational observability, combinational controllability is completed, then we can find out the combinational observability. So if you simple trick guys, if you want to calculate combinational controllability, so we will move from front to back. If you want to calculate combinational observability, we will move from back to front. So it is the simple trick in order to calculate the combinational controllability and observability for a given circuit. So let's see how to calculate combinational observability for this circuit. Okay guys. So initially, according to the rule, the primary output value is assumed to be 0. So let's see, the primary output value is assumed to be 0. Combinational observability of primary output value is assumed to be 0. So it's a rule. So according to the table, if you want to calculate combinational observability for a, so it is a AND gate. G3 is a AND gate. AND gate, the formula is we have formula is sum of output observability comma 1 controllabilities of other inputs plus 1. So it's a formula. So if I wanted to calculate combinational observability of OZ1, so that means at this particular node, that means combinational observability of OZ1. So what's my formula? Sum of output observability. Output observability is 0. 0 plus 1 controllability of other inputs. Means it is a 0 controllability. It is a 1 controllability. So other input is OZ2. That means you have to consider this 2. 1 controllability of other input 2 plus 1 3. 3 will be the observability at this node. So next, combinational observability of OZ2. Combinational observability of OZ2. So it is same AND gate. Sum of output 0 controllability is 0 0. 1 controllability of other input. 1 controllability of other input means, so this one 3. Okay, 3 plus 1. That means 4. Here we can get 4. 4 is the observability, combinational observability. Okay, fine. Here it is at this we can get 0. At this point we can get 3. So at this point combinational observability is 4. So what is this at this point? At this point, for a NOT gate, the formula is, for if you want to calculate combinational observability, formula is output observability plus 1. What is the output observability here? 4. Output observability plus 1 means 5 is the observability at this point. So in similar manner, I have to find out the combinational observability of I1 and I2. Okay, combinational observability of I1. It is also AND gate. We have to follow the same formula. So minimum of input 0 control, so minimum of input observability, minimum of that means sorry, for if you want to calculate observability, the formula is the sum of output 0 controllability and 1 controllability of other input. So see here, what is the output controllability here for this circuit Z1? 3. 3 plus 1 controllability of other input. If here I am calculating I1 now, that means 1 controllability of other input is 1. 1 plus 1 means 5. Here I can get 5. Okay, so next one, combinational observability of I2. That means output controllability. Controllability for this Z1 is 3. 3 plus 1 controllability of other input. 1 controllability of other input means I1. I1 1 controllability is 1 plus 1 according to the form 5. Here also we can get observability is 5. But if you want to calculate observability, I will move from back to front. So in this way I can find out the combinational controllability and observability for a particular circuit. So in examination point of view, mostly you can expect this type of circuits which consists of nearly 6 gates. It is the example too. So if you want to practice, you can practice. Okay, simply, so it is self-explanatory. So I will randomly explain this example. You can solve this particular example completely. So here it is a solution of this particular example. Here it is the solution. These are the combinational observabilities. So all these are the combinational controllabilities for this particular circuit. So it is a solution. So initially for a given circuit, initially I have to assume for primary input, so I have to consider 1, 1, 1, 1. So for all primary inputs, I will consider 1, 1, 1, 1, 1, 1 respectively. So it is a default value I can consider. Here also 1, 1. All these are the primary inputs, right? Primary inputs. So if I want to calculate here, what is the combinational controllability for a NOT gate? Is here 1, 1. That means here it is combinational 0 controllability and combinational 1 controllability is 2, 2 for NOT gate. Here also 2, 2. Why? Because 1, 1 is the default input for this NOT gate. Okay, here 1, 1. Here 1, 1. So here what is that 2, 2, 2 are the combination 0 and 1 controllabilities of AND gate. So what's the formula according to the table? So formula is minimum of input 0 controllability. For 0 controllability, minimum of for input 0 controllabilities plus 1. So for it is a 0 controllability. For 1 controllability, sum of input 1 controllabilities plus 1. That means minimum of input 0 controllability. These are the input 0 controllabilities. Minimum of 2, 2. 2 plus 1, 3. Okay. So next one controllability. Sum of input 1 controllability. These are the 1 controllability. Sum of 2 plus 2, 4. 4 plus 1, 5. Okay. Here it is. So this is transferring here. That means here it is 3, 5. Here it is 1, 1. Here it is same. This node. Here it is also 3, 5. If I want to calculate combinational controllability of this particular, so it is a NOR gate. Combinational controllability of NOR gate. For 0 controllability, according to the table, the formula is minimum of input 1 controllabilities plus 1. It is for 0 controllability. So for 1 controllability, sum of input 0 controllabilities plus 1. So see here, minimum of input 1 controllabilities. Minimum of 1 input controllabilities are see here in this here 1, 5, 1, 1, 5. What is the minimum? 1, 1, 5? 1 only. 1 plus 1, 2. Okay. 2. So next one, for 1 controllability, the formula is sum of input 0 controllabilities. Input 0 controllabilities is 1, 1 and 3. 1 plus 1 plus 3. 3, 4, 5. 5 plus 1, 6. 2, 6 is the combinational 0 and 1 controllability of a NOR gate. So here it is 2, 6. If 1, 1, 3, 5 are the combinational 0 and 1 controllabilities, we can get, so it is a NOT gate, so it is a simple AND gate, we can get 2, 7. Here I can get 2, 7. So here it is OR gate. For OR gate, for zero controllability, the formula is minimum of input zero controllability. So just ulta. Minimum of input zero controllability is plus 1. It is for zero controllability. For one controllability, minimum of input one controllability is plus 1. So it is one controllability. So according to this formula, we can get 5 comma 7 here. So it is a just a self-explanatory. In this way, we can calculate combinational controllability. So if I want to find out combinational observability, I will consider 0 here. From back to front, I will consider find out the combinational observability for the same circuit. It is self-explanatory. If you follow this example by your own, you can easily understand. Thank you guys. Thank you.